Welcome everybody, welcome to tonight's lecture. My name is Jenny Richards. I'm strangely from the School of Literature, but I'll explain that in a minute. I have a bit of housekeeping to get through. Please can I ask that you keep your phones on silent for this lecture. We're not expecting a fire alarm, so if the alarm goes off, please follow the instructions of the event stewards and make your way out of the building to the car park. Please be aware that the lecture New Voices on Arts, Humanities and Social Sciences on Thursday, the 11th of May, has been cancelled. At the end of this lecture, I'll let you know what is the next lecture. If you would like to tweet about tonight's lecture, please use #InsightsNCL. And finally, my last housekeeping item. Following the lecture, there will be an opportunity to ask questions. Now I'd like to introduce our speaker. I have this great pleasure to do that. I'm going to give you an official, the formal introduction, and then I'm going to say a few words about Paul myself. Paul Watson is Director of the UK's National Innovation Centre for Data and Professor of Computer Science at Newcastle University. He's also a Fellow of the Alan Turing Institute. He began his career at Manchester University before moving to industry to help design a product based on his research. In 1995, he joined Newcastle University. That's the same year I joined, actually. He now leads the National Innovation Centre for Data, which plays a key role in enabling private and public sector organisations to exploit data and AI. Paul Watson is a Fellow of the Royal Academy of Engineering and received the 2015 Microsoft Jim Gray Award for eScience. So I think, as you can see, that he's a very distinguished person, exactly the right person to be talking to us today about AI. But I also wanted to say a few words about Paul, because I've been here as long as he has. I hadn't realised that. But he's a very important connector within the university, a really humane and kind and committed listener to other people. I wanted to say, really, to honour Paul. He's been a very important person in terms of changing the way I think about how the humanities might have something to say about the digital revolution. And so I'm going to hand you over to a very highly esteemed colleague. Thank you.
Okay, well, thanks, Jenny, for that. So no pressure now. Thanks to Jenny for those kind words, and to Umberine and Stephanie and the team for organising this, and all the publicity that there has been this week about AI. Every single time I put the radio on and listen to the Radio 4 News, every day this week there's been a new item about AI. There's such a buzz about it at the moment, and the particular nadir for me was on Monday night when I was woken up at midnight by my wife, because the headline of the Monday midnight news on Radio 4 was again about AI, and she didn't want me to miss it in case it was something pertinent to this talk. By Tuesday, I just wish that everybody would just shut up until the weekend. So I'm an engineer at heart, and so my aim is that you'll go away understanding something about how these new AI systems are designed and built and deployed, but also, as it says in the title, not just the opportunities that they present to us, but also the threats that they create. And I think before I get on to the very latest, greatest things which have been in the news this week, then I think it's worth thinking about how we got here, something about the history. And sometimes people say that, well, AI started about 2,000 years ago with the Greeks, who used to write myths in which sculptures would come to life, usually by having gods or goddesses that would breathe life into them. And then through the centuries since then, every new wave of technology that has come along, people have considered whether this could be the start of producing a machine that could compete with humans. And so that goes through the invention of clockwork and precision engineering, which led to people thinking about the design of automata, and then through to more recently, after the Industrial Revolution, wondering whether steam or electricity could drive the creation of machines that could outperform people. And I rather like this picture which I put on the slide here. So this is from 1921. It's by Hannah Hock, and she'd been observing workers in factories in Germany, and she started to think about, as she put it, whether the ideal worker could be a machine. And you see she's drawn a tool maker with a machine, but the tool maker's melded into the machine and become a robot. And so through history, people have pondered whether these technologies could actually lead to intelligent machines. But in the main, it's all been science fiction. Very little science, in fact, very few advances, until the middle of the last century, when a new type of machine came along and sparked a whole new interest in AI. And of course, that machine was the digital computer. And this is a photograph of the very first working modern computer. It ran its first program in July 1948 at the University of Manchester, where, as Jenny mentioned, I started my career a bit after 1948, but still not so long after it that one of the two main inventors of this, Tom Kilburn, he wasn't head of department anymore, he just retired, but he still used to come to departmental reception. So there is a personal link there to this machine. And this was called the Manchester Baby, and it was a very slow, by modern standards, machine with very limited capabilities. So about 128 numbers it could store, which is about 1 billion times less than my mobile phone and probably the phones that you have as well. But as soon as it had appeared, then people started to wonder whether it would be possible to write programs which could mimic the sorts of tasks that humans could do. And in fact, only 2 years after this, Alan Turing started to write papers about AI. And the sorts of things that were the hallmarks of human intelligence, which people like Turing wondered whether we could write software for machines like this to do, were things like visual perception, speech recognition, decision making, and language translation. So this sparked off a whole wave of interest in this area. And over the following years, then hundreds of thousands of very clever people in academia and in industry have devoted their lives to working out how to write that software, what that software could be, which would start to compete with humans on tasks like those. And industry has pumped in hundreds of billions over that period. And actually, it's not gone as smoothly as anybody expected. So Turing, in 1950, wrote a paper where he thought that artificial intelligence would be achieved within 50 years. So that was the year 2000. And obviously we're not there yet. There's been some progress, but there's been a lot of ups and downs on the way. And my career actually started at Manchester. I was given a lectureship there because there was a wave of interest in AI in the 1980s, which some of you here might remember. And this was sparked by the Japanese. And there was the Japanese 5th generation computer program. At the time, the Japanese were considered to be the world leaders in technology. And there was a real fear in the US and in Europe, including the UK, that if the Japanese cracked the problem of AI, then the West could never catch up. It would be so far ahead and be rattling on, increasing the gap between what the Japanese companies could do and what the rest of the world could actually achieve. And so for that reason, there was a lot of investment in the UK, largely through the ALBI program, if some of you might remember that. And what I wanted to do was to show you the sorts of ways in which, in the 1980s, AI was being designed and built. So here's a very simple example. So this type of AI was called Symbolic AI. It was built on logic and mathematical reasoning, which had been developed over the centuries. And I'll show you through a very simple example. So this is a bit of my family tree. I have the advantage of being an only child, so it's not a huge family tree to use for an example. And what you can see is in the family tree, you can see the relationships between various generations, and we can capture that in the way in which it would have been done in the 1980s as a set of what were called facts. So you can see the parent relationships here, which I've captured on the left. So it shows that Bob was the parent of Paul, Jean was the parent of Paul, Paul was the parent of Ben, Paul the parent of Sophie, Andrew the parent of Ben, Andrew the parent of Sophie. So this was one half of what Symbolic AI did to represent facts. And what happened then, of course, is that we can add more facts. So if I was to ask you as humans, are there any more facts you could get out of this tree? One might be that you could do with almost without thinking would be grandparent relationships. You could start to write down some other facts. But of course, you're not doing that just by thinking about facts. What you have in your head is a rule or a set of rules which allow you to infer new knowledge. And what Symbolic AI did, the other part of it, was this. So it had a way of representing rules, and I put one for the grandparent rule in the red box. So all that this says is that GP, that's a symbol which represents a person. GP is a grandparent of GC, another person. If there's a parent relationship, parent fact, that GP is the parent of some X, some person which we'll call X, and then X is the parent of some person GC. So once that rule had been written down, and this is in a language called Prolog. If anybody wants to go home and try it, you can download free versions of Prolog and play with it. So once that rule has been written down, then the system could rattle away and infer new knowledge. And it can infer the grandparent relationships, Bob being the grandparent of Ben, Jean being the grandparent of Ben, and so on. So that was Symbolic AI. And there was an enormous amount of investment put into this by the Japanese, the Americans, and the British in the 1980s. And how did it go? Well, what happened was that people spent an enormous amount of time trying to elicit facts and rules from experts. So they would sit down, you may remember expert systems, some of you. So you'd sit down with somebody who had expertise in the domain, be it a lawyer, an accountant, an English professor, and you would sit down and you would elicit from them the facts that were pertinent to that domain and the rules which allowed new knowledge to be inferred. But this didn't work very well in practice, and that was for two reasons. So the first reason was that it was very time-consuming and very error-prone to elicit facts and rules from experts. And the second reason is that the world is a very messy place. And so trying to capture everything in such a formal system didn't work for a lot of real-world applications. And so what happened was that companies stopped investing. Research councils in all the countries in the world stopped investing in research in universities in this area. In fact, this was about the early 1990s when this happened. And the atmosphere was so chilly for AI that this became known as the AI winter. And it was very difficult to get research funding to work in the area of AI once this had happened. And I'll try to get you to think about why this might be a problem. So here's an example of something that we want to do. So this is when you're driving. I'm sure most people here are drivers. When you're driving, you can do this automatically. Without thinking, you can identify the key objects that there are out of the windscreen, and you can label them if you need to do that. You can tell the difference between cars and trucks and traffic lights and so on. Now, imagine that I set you a challenge, or let's make it even higher stakes. So let's say Elon Musk hires you, and he hires you to write the software for a Tesla. And what he wants you to do is to use symbolic AI in order to infer the different objects on the road. Okay, so think about what facts and rules you might use to do that. So in abstract terms, I didn't show you that image. If I asked you, how would you write facts and rules about a car? You might say, well, cars have 4 wheels, apart from the ones that only have 3 wheels. And then you might say, well, the difference between a truck and a car is that cars are smaller than trucks. But that doesn't really help you here. So you can see that for this, everybody would identify that as a car, but you can only see 2 wheels. This one over here, you would identify that as a car, but you'd only see 1 wheel. And the idea that perhaps you think that cars are smaller than trucks, but if you look at the cars that are in the middle distance over, let's say this one, which isn't particularly big, but it's still bigger than some of the trucks that are in the distance in this image. So it just proved really difficult to try and capture knowledge about the messy real world, and this is why there was the AI winter. Luckily, some researchers kept going at this, and one of them, the main person in this area who was in the news, that's why I was woken up at midnight on Monday, it was because a man called Geoffrey Hinton, he kept going with his ideas, and his group came up with some new advances in AI, which are what has driven the current interest in it today. And this is a different sort of AI, very different to symbolic AI, and this is called connectionist AI. And I'm going to explain this in three or four slides. So the idea of this is you have a network. The circles on here represent what are called neurons, and then you can see the connections between the neurons as the lines. And this whole approach is called deep neural networks. And what happens is that you start on the left-hand side in this image with an image of a car. So this is just one of the ones I took from the previous slide. And as those of you who do digital photography or buy TVs or monitors for your computers know, the way in which images are represented in a computer is by having a grid of pixels, and each pixel represents one dot in the image, and you represent the color by 3 numbers, which are the intensity of the red, intensity of the blue, and the intensity of the green, because those are primary colors, and so by mixing those together, you can form any color that you want. So these pixels then feed into this input layer, the layer on the left of the network. And what these neurons, as they're called, do, you can guess why they're called neurons by analogy to what's going on in our brains. What they do is they take the inputs, in this case the colors, and they apply a function to them, and then they send out the result of that function to the neurons in the next layer, which is called here hidden layer 1. And what those neurons do is to sum the inputs, which are coming from the input layer, apply the function, and then send out the number which is produced to the next layer, hidden layer 2, and that goes on to hidden layer 3, and then you can see that on the output layer, there are only 2 neurons. And this is because, in this example, all we're trying to do is tell the difference between cars and trucks. So we have 1 neuron for cars and 1 neuron for trucks. And what happens is that if you look at the output from this neuron, which I've labeled car, if that is a car on the left-hand side, then if this works, if this deep neural network works, the number that comes out of that car neuron will be very large. If it's a truck that's the image, the number that comes out of that car neuron will be very small. And the reverse will happen for the truck neuron. So by looking at the value, the number that comes out of those output neurons, you can get the deep network's classification of what that particular image is. If I dive into, lift the lid on one of those neurons, so this I promise is the only slide that has any maths on whatsoever, and it's GCSE level maths, so don't worry about it. So what's happening in a neuron is you can see there's a set of inputs coming in, and each of those inputs is then multiplied by a weight. So those are W1, W2, W3, and then these are summed together and added to this weight, which is labelled B. That weight labelled B has nothing to do with any inputs, it's just a fixed number that feeds into this addition. So all of these are added together, and then the output of the addition goes to this function, which then creates another number, which is then sent out to the neurons which it's connected to. And if you're interested in the function, there's a variety of them that you use, but it often looks something like this, a nonlinear function like this. So this is all that this system does. It takes numbers in, it multiplies those numbers by weights, adds them together and applies a function, and sends them out to the next neurons, which do exactly the same thing. So an obvious next question is, well, but how does it work? How is it that if we show an image of a car as in the previous slide, then that car neuron produces a high value as an output? And the reason is that we can do that by adjusting the values of these weights. So these are the only knobs that we can twiddle in this deep learning network. So if these weights are small, that means that the influence of this input on the output of this neuron is very small. If that weight is large, then because you're multiplying it by the input, it magnifies the importance of that input as far as the output is concerned. So that's why we can build deep neural network systems which can do things like classification. But how do we set the value of those weights? So this is where the new advances in data science and AI have come in. It's because of mathematical algorithms which can automatically set the values of those weights. So I think that there's no clear division as to why some things are called AI and some things aren't, but the reason here is because it's not a human who's setting those weights, it's a mathematical algorithm. And this algorithm definitely isn't GCSE maths, and so I'm not going to try and go through it here, but just to explain the process that's gone through, what you do is you have a whole set of examples. In this case, you need examples of cars and trucks and other things, perhaps hundreds of thousands of these. And for each of these examples, they are labeled with what that object is. So in this case, picture of a car at the top would be labeled to say that it's a car, and so on for all of the other ones. And then what happens is an iterative mathematical algorithm which works away in order to optimize the values of the weights across this whole network so that the optimal values of the weights are produced in order to achieve whatever the task is. In this case, to differentiate between cars and trucks. And this is called machine learning, which is a term that you'll have heard a lot about on the radio this week probably, or sometimes deep learning when it's applied to these deep neural networks. So this is the reason for all of the excitement in AI over the last 10 years. The method of mathematically calculating the values of these weights to achieve a particular task was invented by Jeff Hinton and his group in about 2012, and everything else has exploded from there. You might be wondering, well, what's really going on with these neurons? And it seems that what's going on is that as you look from left to right across the layers, I've only shown three of them here, but what the neurons are doing is initially they're coming up with progressively more complex representation. So on the left, the neurons are really just being fired. They're producing high outputs when they see different sorts of edges in the image. So vertical lines, horizontal lines, diagonal lines. By the time it gets to the middle layers, then they're starting to recognize individual features, in this case of cars. So you can probably see some fuzzy wheels, maybe some windows and some doors in there. And by the right-hand side, these neurons are starting to give you representations of the cars themselves. So it starts from a very basic set of features, and then builds up to the whatever the objects are that you're trying to get the system to classify. So this is, once you've done that, once you've done the machine learning, then you've got this network and it's fixed. You don't have to do any more learning, and you can put it on a very simple, cheap computer in a car. So this is just a computer with a camera pointing out of the windscreen of a car, and you can see that in real time at 30 frames a second or 60 frames a second, it can do classification of the objects that it sees out of the windscreen. Okay, so there's a stop sign, so hopefully it'll stop. Yeah, here we go. Turn right, and so on. So this is the first stage in producing autonomous vehicles. There's lots of other stages to happen after that, and they haven't all been cracked yet, which is why we're not all driving around while reading the newspaper or looking at our phones. But this is the first stage, identifying the key objects on the road. Now, the example I've given here is a sort of a futuristic sci-fi sort of example, but really data science and AI are transforming the economy and society across many domains in lots of less glamorous areas. And I want to just give you some examples of that. So this is the National Innovation Centre for Data, which is based here at the university. And our job is to work with external organisations in the private sector or the public sector in order to help them to adopt data science and AI techniques in order to transform what they do. And that might be by getting new insights into their products and services. It might be to improve their productivity. It might be to launch completely new products and services. And so this is the team that we have of data scientists and people who support the data scientists. And across the team, we've got a lot of skills in AI and machine learning, but I just want to point out the other sorts of skills which are very important. So one is statistics. So if you can use old school statistics in order to extract value from data, then it's better than AI techniques, because the statistics tend to be very rigorous and you get an idea of the level of uncertainty in the analysis that you're doing. And I'll come on to that in more detail later. So we've got a lot of statisticians in the group. Then we've got people who do data engineering, because if you've got data streaming in from sensors or from cameras at a tremendous rate, or you've got these huge corpuses of data that you're using to train your models, then you need people who can understand how to build these large computer systems which can handle that. And then finally, visualization experts. So this is important because if you're trying to convey information to humans as a result of analysis so that they make better decisions, then you're better off using visualization rather than, say, giving them an Excel spreadsheet with a huge table of numbers. Visualization can highlight the things that are important, and people can then make better decisions. So these are the skills that we have. And as I said, we work across a whole range of domains. And I just wanted to show you some of the examples of the sorts of areas that we're working in. So on the left, this is an SME that we've been working with, Nebula Labs. And when we work with an organization, we are working with them on a project. And the idea is that our experts, most of our team are PhDs in some aspect of data science. Our experts transfer knowledge across to that organization by working with them on joint projects, so that by the end of the project, they've developed new skills which they can then apply. So our hope is that we can kind of make ourselves redundant, because we can transfer skills into these organizations, so then they can then run with data science. So Nebula Labs been working with the Cobalt Business Park, and what they wanted to do, Cobalt wanted to do, was to understand patterns of traffic and make plans for future transport for people who work there. And so what they wanted to do was to have an app which would collect data as people commuted and then send it into a system for analysis, so that over the whole of Cobalt you get an aggregate view of how people were arriving at work. Now what they wanted to do was not to have people to have to do lots of entry into the app. So right, I'm starting my commute, I'm on a bus, it's finished now, because people get bored with that and fail. So what we did was to work with them so that the app would automatically work out that they were commuting and automatically use machine learning, work out what sort of commute they were doing. So whether they were walking, cycling, on a metro, on a train. So we transferred the AI skills to allow them to do that. The next one, Procter & Gamble, so other extreme, a big multinational. They're, like many companies, they have websites where you can type in your opinions on their products, good or bad. And until a few years ago, what had to happen then was that humans would have to read everything and then work out how to classify it. So what we worked with them on was a way to use machine learning and data science in order to automatically extract the key entities from the text. So in this case, it's the products that Procter & Gamble sell, which people were commenting on, the particular features that they were interested in, and the nature of the comment. And then once you pull those out, you can quickly do an automatic analysis across many thousands or tens of thousands of entries that people have made onto the website. The next one, the NHS Business Services Authority. We do a lot of work with the NHS. Of course, the NHS collects a lot of data and is trying to use it in order to transform the way it works. The NHS Business Service Authority looks after about 35 billion of funding of the NHS. And so what we were working with them to do was to better analyse what the money was being spent on and look for opportunities to target it more accurately. The next one, and again, another end of the spectrum. So this was some work that we did in COVID with the Newcastle West End Food Bank. So this is one of the country's largest food banks. And in COVID time, they had about a 50% increase in the number of clients who were coming to the food banks. And so what they wanted to do was to understand better those clients and where they were located, because of this increase in demand. They were interested in whether to put in a new depot somewhere around Newcastle, but the question was where. So by analysing the clients and where they came from and what their needs were, we could help them to understand where the best place was to locate a new food bank depot. And finally, an example from commerce. So this is an example from, in this case, Newcastle Building Society, but it's a fairly typical example across both e-commerce and also companies which are selling through shops, in this case through building societies. And what they're interested in was, can you predict in advance whether a client was likely to leave your business? And if you can predict that early enough, then you can take action to encourage them to stay. So rather than just wait until they decided to leave and then try to persuade them to stay, if you can predict that in advance, which is what we work with them to do, then you can take action. And this is a very common pattern of work in data science that we've done with lots of organizations now. So these are 5 examples out of 80. So we've run 80 projects with different organizations over the last 4 years. But I hope it gives you an idea of it's not all the whizzy sci-fi self-driving cars where data science and AI is making a difference. It's becoming important right across all sectors of the economy and society. But looking to the future, because we're a university with researchers who are trying to design the future, then we do a lot of work with our medical school. And there's a lot of interest in how data science and AI could transform healthcare. And this is this badge that we put on it, Care Everywhere. And the idea is that we want to move away from the way things work at the moment, which is where typically a patient has to go into a clinic or into a GP to be examined. And they do that when there's a problem or perhaps at a regular interval. And the idea is if you could monitor patients in their ordinary lives, then firstly you'd get a much better idea of how they were behaving, how much the conditions they were suffering from were affecting them. But then secondly, there's an opportunity to sort of turn around that model of the way in which the health service works at the moment, which would be that the system could alert a medic if it was felt it was worth the medic calling in the patient, because they needed to change their drugs, or they needed stronger drugs, or they needed a different sort of treatment. So the way this works is that data from sensors comes into the system. Some of them are apps and smartwatches, but we do a lot of work on gait analytics. So this is some work led by Professor Lynn Rochester in the medical school. And gait analytics, the way in which you walk, it tells you an amazing amount about people's conditions. You can do things like you can classify what condition they're suffering from just from the way people walk. And for people, for example, with Parkinson's or multiple sclerosis, you can see the progression of the problem over time because of changes in the way in which they walk. So that could be an indication that it would be good for a medic to call in the patient in order to get new treatment. And at the moment, the main vehicle for this, or I should say we also combine it with information from medics and also sometimes patients self-report on apps. So this all gets copied into our system and we analyze it in order to understand what's going on with these patients. And to give you some idea of scale at the moment, this is a pan-European project, EU-funded project called Mobilise D. It's led by Lynn Rochester. And at the moment, we've got 2,400 patients who are spread around 10 countries around Europe. And they're wearing the sensor you can see at the top. They wear that in a belt in the small of their back because that's the best way to capture information about somebody's gait. That all streams into our platform. We've ended up, well, at the moment, we've got about 100 terabytes of data. So that's a very large amount of data. So it's always hard to give people an idea of what that means. But I'm running this from a fairly typical laptop here. And you would need 400 of those laptops to store that data. And if I was to do the analysis that we do on my laptop, it would take about 9 years. So what we have to do is we have to go into the cloud where we can access lots of servers, spread the work out across those servers, do the analysis, and then bring it back again. And that means we can do it in about an hour rather than in 9 years. So this has all been quite upbeat so far in this talk, but as you saw in the title, it did say opportunities. So we've almost finished those, and it said threats. So I now need to say something about some of the challenges and the threats which these sorts of systems are introducing into society. So if I come back to AI and I come back to machine learning, then one of the issues is generalization. So remember I said how machine learning worked. We have this large corpus of data, these images that are tagged, and we run those through this algorithm to fix the weights on this deep learning model, which we then use to do classification. Now the issue there is, how do you know that everything that system sees will look like one of the images or something like one of the images that it's been trained on? And here's a nice example of this. This is by some researchers at a company called McAfee. And what they did was they discovered that if you extended the middle bar of a 3 on an American road sign, then Teslas, the software in Teslas, thought it was an 8. And so they did this twice and then stopped. But the car accelerated to 85 miles an hour. They proved the point by then. Didn't want to do it again. And that's because in training this model in using machine learning, then the set of images that they used, probably none of them had an elongated bar on the 3 or anything like it. And so the system didn't generalize enough to decide that that was a 3 rather than an 8. Now you might think this is a very artificial example because who's going to go around and stick black tape on road signs? But you can imagine somebody for malicious reasons might choose to do that, or it might be just that the road sign fades, or maybe it gets dirty. And so this is this problem of generalization. We really don't know what happens once you get away from the standard set of images which you're using to train these models. And so what do we do about this? Well, in the National Innovation Centre for Data, we have to go through a process when we consider using machine learning to worry about generalization. So firstly, we have to think about whether the training set is sufficiently diverse to promote generalization. But then for ethical reasons, you also have to ask the question, what happens if it goes wrong? What happens if there's a mistake? is it worth taking the risk of using these methods for this particular application? So we always have to go through that process because AI systems aren't as reliable as we'd like them to. The next example, which I'll come to, is bias. So this is, you'll have probably heard quite a lot about this. So this is the problem that the training set that you use, if that has bias in it, then that bias is going to be embedded in the neural network, which is created through machine learning. So here's an example which I rather like. So this is using Google Translate. I'm sure a lot of us have used this to work out menus in foreign restaurants. And so you can type in this case, this is Hungarian to English. So how will this network have been trained? Well, what will have happened is that they'll have gone out over the internet and they would look for pairs of documents where one of them was in Hungarian and the other one was the English translation. And then they would have fed this into a machine learning algorithm so that it was able to make the links which allowed it to do the translation. But you can see what happens here. So this is a particular problem in Hungarian because Hungarian is a gender-neutral language. I don't know whether there's any Hungarian speakers here. Oh, really? Oh, fantastic. So can you read out the first line of that for me, please?
Well, half Hungarian, we can try. Szép, okos, olvas, mosogat, épít, vár, tanít, bőz, kutat.
Thank you. Okay, that's perfect. So I'll have to take you around to all the lectures I give in order to read out this slide when I come to it. So, but you can see what the problem is. So when it gets translated into English, then it's very sexist, isn't it? So she is beautiful, he is clever, he reads, and yet in the Hungarian there's no idea of gender. And so, you know, thinking about why this happens, it's not that Google have employed a huge team of misogynistic data scientists in order to build out these translation systems. It is just because if you look at the data that was used to train it, the extant data that's out there on the internet, then these must have been the translations. And I like the last line, which is presumably perfectly translated as "Go to hell, Google," which Dora Varga has used here. So this is a real issue. Bias in the training set gets embedded in these networks and gets amplified because everywhere you use this, you have that bias. And so again, what we have to do is, when we're considering using machine learning, we have to ask, is there bias in the training set? Is there something we can do to ensure that it isn't biased? And then secondly, we have to ask that question again, what's the consequences of deploying this application if there is bias in it? Is it worth the risk? Now, until about 2 months ago, I thought that I'd now end and give some conclusions. But given all of the flurry of interest in AI over the last 2 months, eventually I had to crack and add in something about large language models, ChatGPT-3 and so on, which has really been the subject of almost all of the discussion over the last week or so in the press. And large language models are just very large deep neural networks, so of the sort which I've talked about, but they are huge. So you can see there 11.5 billion neurons, 175 billion weights. And so remember that you have to set those weights using this mathematical procedure, all 175 billion of them, and it takes about a month to do that. So the machine learning takes a month on 1,000 computers, and if you cost how much those computers cost, it's about $4.5 million every time you train this. And it's trained on text from the web, Wikipedia and books, and it's a language model, so it's working on words. It's not working on numbers, it has no mathematical capabilities, and there's 500 billion words in that training set that it uses. And what it's trained to do is something like when you've got your mobile phone and you're texting, and it's giving you a suggestion for what the next word is, then that's really all it's doing, except it's got this huge engine that's created this network. And it doesn't just predict one word, it doesn't just stop and give you an option, it produces that as an output, and then the next word, and then the next word, and it just keeps going until it's finished its task. So, I've been playing with this like a lot of people have, and I wanted to give you 2 examples. So, I have a friend who is a TV producer, and so at Christmas we were having a go together at playing around with ChatGPT 3, and I was saying to him, well, maybe we could write scripts for your programs using ChatGPT 3. And so this is what he is the producer of Malory Towers, which some of you might know is a children's TV program on the BBC. Some of you may remember it as a set of Enid Blyton books from long ago. But the only thing I wrote into ChatGPT 3 was write a Malory Towers script about one of the girls falling down a well. Okay, and it actually produced 4 pages of script. And it's got the names of the girls right, it's got the setting right, it knows it's in a school, and there is a narrative arc. This is only the first page, and I'm not going to go through it all, but the girls go out into the playing fields, one of them falls over. When she falls over, she's near a well, she looks down the well, sees there's a girl down the well, goes and gets help. They manage to get the girl out of the well. They go back into the school. The headmistress has a special assembly where she congratulates them for rescuing the girl and warns them about playing near the well. So we were quite astonished that it managed to do this just from that one-line prompt. The conclusion we came about whether you could turn this into a TV program was that you couldn't. It's not very rich in terms of its language, and the story's a bit dull. There is as I say, there is a narrative to it, but it's just too straightforward. But we were both impressed by that. And so the feeling we had was not that this was ready to write whole TV programs, but maybe it could be used to spark creativity. So maybe you could use this to give you some ideas, and then a team of professionals could work with it. Another thing which I came across, and this wasn't me this time, this was somebody on Hacker News, was there's a lot of interest in can you use ChatGPT 3 and so on, these large language models, to do research for you. So as you can imagine, in a university, there's a lot of worries about how students might use these sorts of systems to do essays or to do their research. But you could see this might be useful. So the prompt was only please provide references to do with mathematical properties of lists. I know there's some people in the audience who might be interested in being able to type in those sorts of questions and getting answers. But it produces 5, so 5, and rather nicely, instead of just giving you the titles and the author, it gives you links to them so you can just click through. But if you click through to any of those, you get a 404 error, there's nothing there. Or you get a link to a completely different paper or book. And it turns out that all of these are made up. Not one of these references actually exists out in the real world. And so the way in which ChatGPT has worked in trying to predict the next word sometimes takes it off in funny routes. But the problem is it looks really convincing. Yeah, that's the problem. You can imagine people using this for certain purposes, and you could be convinced by it. And there's some examples of this. So some companies, you know, when you go to a website and there's a little chatbot comes up in the corner of the website. It's usually if you're on an e-commerce website and it says, do you have any questions? And you start to type into it and it tries to be helpful. So companies thought, we can replace humans who are doing that and we can just use ChatGPT 3. But then it was found that often the large language model they were using would put out something that was completely erroneous about their products or try to sell people products that didn't exist. Or even in some cases, it would start to insult the customer, which is very bad for trying to sell things. So really, there's a lot of concerns about, and that was really why it's been in the news this week, about the ability to produce convincing but wrong text. And Geoffrey Hinton on Monday night at midnight, what he was worried about was industrial scale disinformation. So you can imagine before an election, at the last US election, there was a lot of concerns about these farms, people, real humans who were typing out erroneous articles, news articles, and putting them on websites, putting them on Facebook, and people believe them. Now you've got a tool where you could churn these out, a million of them every second if you really wanted to. So there's a real concern about disinformation. The other issue about it, of course, is that this sort of nonsense that it's producing will go out on the internet. And then the next generation of these chatbots will use this erroneous material as their training material. So there's a real concern that this is just a spiral of doom for these systems. They're almost creating their own demise, because every iteration will produce more and more erroneous material than before. So this is why these are very new. There's still a lot of debate over them, but inherently they're not going to give you accurate answers all of the time. But the problem is, when they don't give you accurate answers, they're very convincing in doing that. So the issue is, how do you tell the difference? And what you need for that are humans who can look at what it's produced, as this person here did, and see that these books didn't really exist. Okay, so to come to an end, then the first thing I want to, so I started on the optimism, and then there's the doom and gloom, but I did want to come back to the fact that data science and AI are transforming research, industry, and society. And in the National Innovation Centre for Data, we've seen how it can help public sector organisations and private sector organisations to transform what they do, to become more productive, to launch new products and services. But going back to the optimism of Alan Turing in 1950, when he thought that in 50 years AI will have been cracked and we will have a general system which will be able to do what humans can do, we're certainly nowhere near that at the moment. And my opinion is that you've seen the two different ways in which have been the main thrusts of AI over the decades: symbolic AI and then connectionist AI. Symbolic AI had this problem that the real world's messy, you can't really capture it, whereas connectionist AI has this problem with generalization, with the problem of bias, and now this problem of these big deep learning networks which can produce absolute rubbish but look convincing. So I don't think, personal opinion is that neither of these two techniques are going to get us to general AI, and we need to find some other way to do it. And the final thing is, well, what do we do about all of these challenges, which is that these systems are going to be deployed more and more, and they're going to cause us lots of issues. So I think that there's a few things that we can actually do about it. So I think that one of them is regulation, so to make sure that we don't launch into the world things which are going to cause humans harm. I think the second one, though, is that really what we need is that people who are considering deploying these systems need to think about whether it's the right thing to do before they actually deploy them. We don't want people to deploy these systems and find out that they cause societal threats, all sorts of problems to businesses because they haven't thought through the consequences. So thinking at the time when people are considering deploying some application, will there be problems because of bias? Will there be problems because of generalization? Will there be problems because it will produce false information? You need to do that right at the start rather than at the end. And I think that in order to do that, what we need is more education, and that needs to be right across the board. So everybody who has a position of responsibility, or any students who will, from any discipline which will move into positions of responsibility in the future, they need to be taught about these techniques, these methods, and the threats and problems that they can create, rather than just the opportunities and the hype that we often hear. And also the general public. The general public is going to be affected by this. Poor decisions are going to affect the quality of their life. Disinformation could really have a dramatically poor effect on the governance of countries. So the general public also need to be aware of what these issues are. And but the one thing I'm certain of is that we can't just leave it to data scientists like me. We need everybody to be aware of the problems and to engage with them when they're thinking about using these methods. Thank you.